Welcome to the Explainer. Today, we're diving into what I like to call a real-world mathematical superpower. Have you ever wondered how massive companies make those impossibly complex decisions to maximize their profits when their resources are strictly limited? Well, spoiler alert, they don't just guess. They rely on a wildly powerful branch of mathematics called linear programming. And to understand exactly how this works, we're going to break down a highly relatable, high-stakes example that just brilliantly illustrates the whole shebang. So, picture this. You're a furniture dealer. Your goal, naturally, is to maximize your profit. But here's the catch. You don't have infinite cash, and you certainly don't have infinite warehouse space. Every single day, business owners are sweating over this exact dilemma. How do you find the absolute perfect balance of investments to squeeze every last drop of profit out of what you have? Buy too much of one thing and you're out of space. Buy the wrong thing and you've burned through your cash without seeing a solid return. So let's look at your options. You only deal in two items: tables and chairs. Tables are your high-risk, high-reward play. A single table costs you 2,500 rupees to buy, but it nets a pretty handsome profit of 250 rupees. Chairs, on the other hand, are way cheaper. They only cost 500 rupees, but they yield a smaller profit of just 75 rupees. So, what's the move? Do you just buy tables because they make more money per unit? Or do you load up on a ton of chairs because they're cheap? Well, to answer that, we've got to look at your harsh reality. You only have 50,000 rupees to invest in your inventory. That's a hard cap. On top of that, your storage space is strictly limited to a maximum of 60 pieces of furniture in total. It really doesn't matter if they're bulky tables or folding chairs, your warehouse maxes out at 60 items. These are the real-world limits we're up against. So to solve this, we need to translate these physical limits into the language of mathematics. All right, let's translate. This brings us to our first key concept: decision variables. We need to decide exactly how many of each item to buy. So let's make X the number of tables we buy and Y the number of chairs. These are our decision variables. And since we're dealing with physical objects in the real world, it's pretty obvious that X and Y have to be non-negative. I mean, you can't exactly buy -3 tables, right? So X must be greater than or equal to 0, and Y must be greater than or equal to 0. Now, what's the ultimate goal here? The dealer wants to maximize total profit. In math terms, we call this our objective function, and we represent it with the letter Z. Since every table, our X, gives us 250 rupees profit, and every chair, our Y, gives us 75 rupees profit, our total profit Z is equal to 250 times X plus 75 times Y. Our entire mission in this scenario is to make Z as large as mathematically possible. But hold on, we can't just magically make X and Y infinity to print money. We're boxed in by what mathematicians call constraints. Constraints are the linear inequalities or equations that act as absolute restrictions on our decision variables. You can think of them as the mathematical walls built out of your limited budget in your limited warehouse space. Let's literally build those walls right now. First up, our investment constraint. Each table costs 2,500, each chair costs 500, and our max budget is 50,000. So 2,500x plus 500y must be less than or equal to 50,000. Actually, if we simplify that by dividing everything by 500, we get a much cleaner inequality. 5x plus y is less than or equal to 100. Next is our storage constraint. The total number of items, x plus y, must be less than or equal to 60. And finally, those non-negative constraints we mentioned earlier, where x and y are greater than or equal to 0. Now, staring at a bunch of equations is, well, it's only going to get us so far, right? To really understand our options, we need to map them out visually. By graphing these specific constraints on an x and y axis, we can quite literally see every single possible choice the dealer is allowed to make. When we graph all these inequalities together, they overlap to create a very specific zone. We call this the feasible region. This is the common, bounded area determined by all our constraints. Every single point inside this region and on its boundary lines represents a feasible solution. That means it's a combination of tables and chairs that you can actually afford to buy and actually have the space to store. Anything outside this region, completely impossible. When we visualize these boundaries, we see a shaded area bounded by the points O, A, B, and C. The line x plus y equals 60 caps our storage, while the steeper line, 5x plus y equals 100, caps our budget. The shaded polygon right in the middle is our universe of valid options. If we pick the point 10, 50, which is perfectly inside, we could afford it. But if we pick 25, 40, which falls way outside, no way, we simply don't have the resources. But here's the rub. Even within that tiny bounded region, there are technically infinitely many points we could choose. So how in the world are we supposed to find the single perfect point that gives us the maximum value for our objective function? We certainly can't plug every single possible number into our profit formula to test them one by one. We absolutely need a shortcut. And thankfully, the foundational mathematics of linear programming gives us exactly that, an incredible shortcut known as Theorem 1. It states that when an objective function has an optimal value, like a maximum profit, subject to linear constraints, that optimal value must occur at a corner point, or vertex, of the feasible region. It's never going to be hiding somewhere randomly in the middle of the shape. It will always sit right on the edge, at a corner. This brilliantly illustrates our path forward, using what's called the corner point method. It's elegantly simple and incredibly powerful. Step 1, we find our feasible region and map out its corner points. Step 2, we evaluate our profit formula, our objective function z, strictly at those specific corners. Step 3, we just look at the results and identify the highest number. Let's do it for our furniture dealer. Okay, let's evaluate the vertices of our bounded region, OABC. Point O is at 0, 0, buying nothing, which naturally yields 0 profit. Point C is at 0, 60. That's buying 60 chairs and 0 tables, giving a profit of 4,500 rupees. Point A is at 20, 0, buying 20 tables and 0 chairs. That uses our whole budget, but leaves the warehouse mostly empty, giving a profit of 5,000 rupees. Not bad. But what about that final corner, point B, sitting at coordinates 10, 50? Let's plug point B into our formula. That means buying exactly 10 tables and exactly 50 chairs. So 250 times 10 plus 75 times 50. The total, boom, 6,250 rupees. Comparing all the corners, 6,250 is the clear, undisputed winner. This combination perfectly threads the needle between our tight investment constraints and our storage constraints to totally maximize our return. 6,250 rupees. That is the absolute maximum possible profit the dealer can make. By translating a stressful, real-world business dilemma into decision variables, objective functions, and constraints, we didn't just find a good option. We mathematically proved without a shadow of a doubt that 10 tables and 50 chairs is the absolute best possible choice. And this leads us to our formal definition of an optimal solution. An optimal solution is just any point in the feasible region that gives the optimal value, either the absolute maximum or minimum, of the objective function. In our dealer's case, the strategy of buying 10 tables and 50 chairs is definitively the optimal feasible solution to our linear programming problem. You know, what is genuinely amazing is the history behind all of this math. This isn't just an exercise for small furniture shops. Linear programming was originally formulated way back in 1941, during World War II, to plan massive military operations, economize expenditures, and optimize complex global logistics. It was so revolutionary that the mathematicians and economists who developed these theories, including Leonid Kontorovich, were actually awarded the Nobel Prize in Economics in 1975. Today, powered by massive computers, these exact same linear programming models are used to solve insanely complex, multivariable optimization problems across global industries, commerce, and management science. But the fundamental logic is exactly the same as our furniture dealer. So as we wrap up this explainer, I want you to consider this. If this mathematical framework can definitively solve a stressful business dilemma by mapping constraints and just finding the corner points, what other complex choices in your work or even your daily life could be optimized just by visualizing the feasible region? Definitely something to think about.